Spatial autocorrelation of an environmental variable, or how similar it is to itself across space, is one of the most simple to compute and useful statistics in environmental science and engineering. Consider a dense river network. We usually want to know, is water quality good everywhere, but we can't measure it everywhere, so we pick a subset of locations along the river network and set up monitoring stations. In the forests of the northeastern US, we have issues with invasive insects and disease, damaging foundational forest tree species. We can't go out and measure the entire forest, so we usually measure a subset of plots and use that to extrapolate. Geotechnical investigation of the subsurface is a critical practice that helps to determine the depth of rock, groundwater, different soil textures. Coring logs can only be developed for a subset of locations requiring interpolation between points. All of this analysis only works if the variable we're trying to measure exhibits spatial autocorrelation. In my time working as an environmental engineer and scientist, I've come to understand that the public doesn't want to spend a lot of money making predictions about the environment when there might not be a problem, and I get it. This makes some sense. The challenge is when there is a problem, society wants our understanding of the environment to be absolutely perfect.
I demand!
A cheap and accurate prediction of water quality. The USGS Surface Water Network does an incredibly good job of tracking water quality across the US. Some basic parameters are usually measured, like specific conductance, dissolved oxygen, temperature, and pH, and each of these plays a vital role in defining water quality. We can see here that some variables, like temperature, are measured much more commonly than something like dissolved oxygen. The reason for this usually comes down to cost. This is a simple handheld air temperature sensor. It does a few other things. It costs about $170. For comparison, this is a handheld dissolved oxygen sensor. It costs about $6,000. And it doesn't just work out of the box. It also needs to be calibrated periodically. So measuring dissolved oxygen is much more expensive and takes more effort. Consider a trout stream where we are concerned with the levels of dissolved oxygen. It might be too expensive to just install a dissolved oxygen sensor everywhere we need one. Environmental scientists are incredibly good at finding practical workarounds to problems. We know that temperature and dissolved oxygen are correlated, where as temperature rises, dissolved oxygen drops. We can possibly then just measure temperature instead of dissolved oxygen. But consider this. This stream might have a problem with high levels of nitrate or ammonia that are driving the growth of algae. Initially, the algae is going to produce more dissolved oxygen. Eventually, this algae is going to deplete the nitrogen in the stream, and when it runs out of nitrogen, it's going to die and it's going to be respired. As it's being respired, microorganisms are going to consume dissolved oxygen and give off carbon dioxide. And in this way, even though stream temperature might be very cold, this other process can drive dissolved oxygen levels down to dangerous levels. So now the question is, can we take this network of measurements from across the US and use it to fill in the gaps in our knowledge? Can we make guesses about the places where we haven't measured dissolved oxygen? In introductory hydrology courses, we teach students that watersheds are basically isolated little units where water quality happening inside of one watershed does not necessarily imply bad water quality outside. However, once we start moving into grad level topics, we talk about the role of society in shaping water quality. And while watersheds might be disconnected from each other, land use tends to be fairly spatially homogeneous. We're going to try and get as much as we can out of this very expensive and difficult to collect data by checking for spatial autocorrelation. So let's say we have a network of 3 data points that we've measured. Because each of these data points has an XY location that exists in space, we can compute the distance to each other point. We're going to set up a distance matrix. We can measure each of these distances, and then we're going to populate this matrix with zeros on the diagonal, and then just fill in the distance from A to B is 1. The next step is to compute a weights matrix. And for the purposes of this example, I'm going to assume my weights are equal to the inverse of the distances. Once we have all our values, we're going to compute first the average of our data, which is just the summation of our data points divided by the total number of data points. And then we can compute Moran's I. So what Moran's I basically is it's a weighted average. We're looking at the covariance of each point to each other point, weighted by the inverse of the distance. So points closer together, we're checking for covariance and giving that covariance a much stronger weight, and then we're summing it all up, and we're going to get a value that goes from -1 to +1, where +1 means they're perfectly correlated in space and it's safe to do the spatial interpolation. -1 means they're perfectly negatively correlated. And values around 0 indicate no correlation. We'll take a snapshot of water quality data from the USGS network from March 2025. We're going to pull it into R, and then let's just compute Moran's I for temperature. And what we get is an I value of 0.7, which is very, very high, and a p-value of 0. So this tells us that water temperature is highly spatially autocorrelated, and maybe doing an interpolation of water temperatures is appropriate. Let's do the same thing for dissolved oxygen. Here we get an I value of 0.5, so a little bit lower than temperature, but still our p-value is indicating significance. Here's where the science gets a little bit fuzzy. We want to do an interpolation for dissolved oxygen because we're really interested in that parameter, but we need to acknowledge that the spatial autocorrelation isn't perfect, so our interpolated dissolved oxygen values are going to carry some error. Let's take a look at our interpolated maps. Higher temperatures at lower latitudes make sense, more solar radiation closer to the equator. Dissolved oxygen, on the other hand, it's a lot more complicated. It's a more nuanced story. We do see maybe higher dissolved oxygen at higher latitudes where temperature's colder, but you can see areas where there are really local hotspots of low dissolved oxygen, and that might be because of another water quality issue. So a spatial interpolation of dissolved oxygen, I would proceed with extreme caution. Have a good day.